Chapter 16, Part 2 is on polyprotic acids. So polyprotic acids are acids that have more than one proton. If it has two, we can call it a diprotic acid. 3, we can call it a triprotic acid, or just in general polyprotic. So sulfuric acid, for example, has 2 protons that it can lose in reaction. So in this case, the starting acid, H2SO4 with water, this is a strong acid, so it's going to completely dissociate or completely donate all of its protons to the water. And what's going to be left is this conjugate base. Now this can also act as an acid and lose that proton as well. So when it reacts with water, it is not a strong acid, it is a much weaker acid. So we have an equilibrium reaction. And then it can give its proton to water as well and be left with this conjugate base. So each of these reactions can be done, they are done sequentially, so they don't all happen at the same time. The first reaction must be done first to then generate this HSO4, which can be used in the second reaction. Okay. Sometimes your diprotic acids are also weak at the start, so like carbonic acid is a weak acid. So it's going to form an equilibrium reaction with water. It's going to lose a hydrogen. That will be a conjugate base. And then it can also act as an acid with water in a weak equilibrium reaction, or it donates a proton as well. So at the end of the day, when this reaction reaches equilibrium, there are a lot of different species that are present. You still have initial H2CO3, you have acid formed, you have some of the conjugate base, then you also have a more H3O plus formed, you also have this CO32 minus, and then of course you all have all this going on in water. So there are a lot of different components that are going on in these reactions. So each of these equilibrium reactions have an associated Ka expression for them. So for the first reaction, we would use these as our products over my reactant, and then for my second one, we would use these as my products over my reactant. So Ka1 would have those on top over my acid. Ka2 would have that. So we just number them. The first one that happens we call Ka1, the second one Ka2. If we have an additional, Ka3, and so on. Okay. Now, if we look at these reactions, if we wanted to measure the pH of this overall reaction of carbonic acid and water, to know the pH, we have to know the concentration of our hydronium ion. But we have 2 different sources of it in our reaction. They're both generating some, so they're both going to contribute to the pH. But most of the time, we can ignore the second reaction. If Ka2 is such a small value compared to Ka1, it means it is only forming a very small amount of hydronium ion. So it's not going to really change the pH by any means. Ka1 is typically larger than Ka2, which is larger than Ka3, meaning Ka1 is the strongest acid. The reaction for Ka3 is the weakest acid. So we can sort of simplify it and just look at the hydronium ion formed in the first reaction. So ascorbic acid is a diprotic acid. So we want to know 2 things about this reaction. What's the overall pH of the equilibrium reaction? And what's the concentration of the ascorbic ion, C6H6O6 2-. So we're going to abbreviate this as H2, and then we're going to call this thing ASC for short, which means this is going to be ASC -2, just to make our writing a little easier. So this is a diprotic acid, so we're going to have 2 reactions. Oh, let's do ASC. The first one with water. So it's going to have one proton left, charge is going to go down one, and then that can act as an acid with water. So in order to know the pH, we need to know the hydronium ion amount. And again, if you look at your Ka values, they are very different. Ka2 is much smaller, meaning only a very small amount of the second reaction forms H3O+. So we can just use the first reaction to figure out the pH. However, in order to do the second reaction, we have to consider both because the AsC2- is only formed in the second reaction. So what we have to do is undergo this first reaction first and then undergo our second reaction. So for the pH, we're going to look at our first equilibrium reaction. So our initial is 0.1 given to us in the problem. Water we don't care about. Initially we have 0 products. So we can complete our icebox to get our equilibrium amounts. The equilibrium constant expression, our Ka, is going to be our products of this reaction and now we can plug in all the things we know. So we know our Ka1, H3O+, and our conjugate base are both x, so x squared. And then our acid is 0.1 minus x. Okay, so the same problem as before. Now we're looking to see if we can simplify by ignoring this minus x. So same idea, Ca over Ka. Is this greater than 100? Our initial concentration of acid is 0.1. Our Ka1 in this case, and it is over 1,000. So yes, we can do this simplification. So we can write our K expression as this to solve for x. So when we work this out and we solve for x, we get this value, which is equal to our H3O+. So now the pH can be determined. .55, or you can do 2.6 if you want to keep it consistent with 2 sig figs. So that's the first question. The second question is how much of the ascorbic anion is formed. So if we look at the reaction that produces it, okay. When we look at this reaction and we do the icebox for this, our starting amounts of our HASC and our H3O+, we have starting amounts of both of those that were determined in the first reaction. Our HASC and our H3O+ were both equal to x, which were both equal to 2.8 times 10 to the negative third. Because remember, this reaction has to happen first, and then now these two things are present when the second reaction starts. So our starting amount for both of these is 2.8 times 10 to the negative third. But we have never formed our ascorbic anion yet, so its concentration at start is 0. This is going to go down as the reaction proceeds, And then this is going to start with some amount, and then it's also going to continue to increase. So it's going to go be plus x. So our K expression is Ka2. So if we plug in all the things we know, what we're trying to solve for is that. So our Ka2 and now we have, can't just have x squared on top because both your two top things are not x. You had a starting amount of H3O plus to begin with. Now this looks scary because there's lots of x's going on, but we can see if this can also be simplified. In this case, we would be able to possibly ignore not only the minus x here, but also the plus x there if x is very small. So we can do the same check for simplification. Is this value greater than 100? So in this case, Ca is our starting amount of our acid. Ka is going to be our Ka2. And I don't remember what it is, but it's like billion range. So yes, it is definitely greater than 100. So we can ignore it. So now on top we have just this, no more plus x times x. And no more minus x, we can ignore that. So now these two things are going to cancel out, making our simplification, our math, much easier. So our value for x is just our value of Ka2, which is equal to our anion that we were trying to find. So if your two Ka values are significantly different, and your very starting amount of your overall starting diprotic acid concentration is not extremely small, then typically you will always see these assumptions. You can consider only the first reaction for the pH or for your H3O plus, and your anion formed from your second reaction is going to be equal to your Ka2, but only if those two things are true. Your Ka2 is much smaller than your Ka1, and your initial amount of acid, whatever it is not extremely small. Extremely small being like to the -3rd or smaller scale.